This is a follow-up of two past uploads on vector products and rate of change of angular momentum, also known as moment of a force or torque. We apply the concept of vector product in determining angular momentum and torque using unit vectors I, j, and k. So students, just hang on, watch, and learn. We are given three particles. Particle 1 has a mass of 2.0 kilogram. Particle 2 has 4.0 kilogram mass, and particle 3 has a mass of 1.0 kilogram. Particle 1 is described by its position vector r of 1 or r sub 1 with respect to the origin equal to negative 2i or 2.0i plus j, and an instantaneous velocity v sub 1 equal to 4.0 j meters per second. While particle 2 has its position vector r sub 2 equal to 4.0 I plus j, and an instantaneous velocity v sub 2 equal to 5.0 I meters per second, and particle 3 has its position vector r sub 3 equal to 2.0 I minus 2j, and with an instantaneous velocity equal to 3.0 I meters per second. And the questions are: letter A, determine the total angular momentum due to the three particles about the origin. And question letter D, what is the rate of change of the total angular momentum? Before we proceed to our computations, we have here a summary of all the data given. All right, so let's have a recap. The mass of particle 1 is equal to 2.0 kilogram. Mass of particle 2 is 4.0 kilogram, and mass of particle 3 1.0 kilogram. The velocity of particle 1 is 4.0 j meters per second. That of particle 2 is 5.0 I meter per second, and for particle 3 the instantaneous velocity is 3.0 I meters per second. Also shown in the previous diagram, the three forces F1, F2, and F3 are acting on each of the particles. On particle 1, there is a force F1 equal to negative 6.0 I Newton. On particle 2, the force is 10.0 J Newton. And on particle 3, the force equals negative 8.0 J Newton. So, before we answer question number or letter A, determining the angular momentum of each particle, okay, we have to identify the linear momentum. All right, the linear momentum p sub 1 on particle number 1. All right, and this is expressed as the product or vector product of the mass particle 1 and the instantaneous velocity of particle 1. So what we have here is P1 equals 2.0 multiplied by 4.0 j. All right, so we are doing a vector multiplication. And the vector product for particle 1 will just be equal to 8.0 j. And determining the angular momentum labeled here as L1, again, we use the vector multiplication or vector product of R1, which is the position vector given here, all right, multiplied by the linear momentum P1. All right, so this formula again requires vector multiplication. Substituting first, okay, R1 is equal to negative 2.0 I plus j, while linear momentum P1 is 8.0 j. So when we do our vector multiplication, okay, when we multiply negative 2.0 I by 8.0 j, all right, the vector product will be equal to negative 16k, right? The magnitude is 16, all right? We get the sign of this vector product with the help of our right hand rule, right? So when you do your right hand rule, okay, you will find out that the direction of the vector product will be along the negative z axis. Okay, the vector product of j cross 8.0j is understood to be equal to 0. That means negative 16k is our final value for the angular momentum of particle 1. And moving on to determining the angular momentum for particle 2, we have here the position vector of particle 2 equal to 4.0 I plus j, and getting its linear momentum P2, which is just the product of the mass of particle 2, which is 4.0 kilogram, and its instantaneous velocity equal to 5.0 I. So doing our vector multiplication, we have P2 is just equal to 20 with two significant figure, right? 20 I. And so therefore, its angular momentum L2, which is just the vector product of R2 and P2, substituting for R2, 4.0 I plus j, to be multiplied or cross multiplied by P2, which is 20I. So 4.0 I cross multiplied to 20I, of course, is also equal to 0. And j cross multiplied to 20I will give us negative 20k, right? The sign negative can be verified again using your right hand rule. Finally, for our particle 3, whose position vector r3 equals 2.0i minus 2j, its linear momentum p3 is just equal to the cross product of its mass, which is 1.0 kilogram, and its instantaneous velocity, b sub 3 equal to 3.0 I meters per second, and we will get it the value of its linear momentum equal to 3.0 I. So its angular momentum L3, okay, R3 cross multiplied by P3, substituting, we have R3 is 2.0 I minus 2J to be cross multiplied by the value of P3, which is 3.0 I. 2.0 I multiplied, cross multiplied by 3.0 I again is equal to 0. So the final value for angular momentum of particle 3 would just be equal to positive 6.0 K. Alright? We cross multiplied negative 2J by 3.0 I. Again, the positive sign of our final answer can be verified using your right hand rule. Question letter E. Our target variable is determining the total angular momentum of the three particles. So what we do is just get the total or the sum, alright, of the three angular momenta that we had earlier. That is, total momentum, capital L, is just equal to negative 16K minus 20K plus 6.0K, and we get the answer equal to negative 30K, the unit of which is kilogram meter squared per second. And this is about the origin. Moving on to question letter B. Which is asking for the total or the rate of change of the total angular momentum. So that is simply expressed as delta L total divided by delta T, or since by definition the rate of change of angular momentum is also the same as the torque, right? So the total rate can also be expressed as total amount of torque, which is just the sum of torque 1 plus torque 2 plus torque 3. So we need to calculate each of the three torques, starting with torque number 1. And torque number 1, labeled here or denoted here by the Greek letter tau, representing torque. Alright? Again, we are doing a vector multiplication. We multiply the position vector R1, cross multiply it by the force F1. Substituting, the value for R sub 1 is equal to negative 2.0 I plus J. Cross multiply it to the value of F1, which is negative 6.0 I Newton. Alright, so we will get the value for torque number 1 equal to positive 6.0 K. Again, you can verify the sign for our torque number 1, why it is positive, using your right hand rule. Moving on to torque number 2. Torque number 2 is just the cross product of R2 by F2. Substituting, okay, R2 is equal to 4.0i plus j, and F2 is equal to 10.0j. So doing our cross multiplication again, we get positive 40k. Alright? When we multiplied j, or cross multiplied j by 10.0j, again the answer is 0. So I only left with 4.0i cross multiplied by 10.0j. That's how we got positive 40k. But the sign why it is positive, you may verify it using your right hand rule. And for torque 3, which is the cross product of R3 and F3, substituting, we have 2.0i minus 2j. That's the value for R3 to be cross multiplied to F3, which is negative 8.0j, and our result is negative 16k. Alright? Negative 2j cross multiplied by negative 8.0j is also equal to 0, so we are only left with the cross product of 2.0i and negative 8.0j. That gives us negative 16k. Why it is negative? You may verify it using your right hand rule. And so finally, if you get the total of these three torques, alright, we just add them. The summation of torque is equal to positive 6.0 k, that's the torque number 1, plus torque number 2, which is 40, positive 40k, then minus negative 16k, which is the value of torque number 3. So therefore, our total torque is equal to positive 30k Newton meter. So we say that positive 30k Newton meter is also the change of the rate, okay, of the total angular momentum. So that completes our answers for these questions. Thank you very much for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.